At the end of the last video, we found a solution to a non-homogeneous system, and we wrote it in the form of x equals x sub c plus x sub p, where x sub c was the complementary solution and xp was the particular solution. I want to focus now on the x sub c part, and it's the matrix of solutions times a column vector of constants. The matrix of solutions is denoted using an uppercase Greek letter phi, and we can represent the column of constants using the vector c. So the complementary solution has the form x sub c of t is equal to phi of t times c. Now that phi is called the fundamental matrix of the system, and the determinant of phi is what we call the Wronskian. The Wronskian's a little bit different when we're working with systems than what we saw before. Because the solutions in that fundamental matrix are linearly independent, the Wronskian is non-zero, so the inverse of the matrix exists. Since phi is a solution to the differential equation x prime equals ax, we know that phi prime equals a phi. We just plug phi in place of x. We're going to propose a form of solution. This is going to feel like variation of parameters that we saw in a previous chapter. X sub p is equal to phi of t times, instead of a constant column vector, it's a column vector of functions of t. So we have xp equals phi times u, where the entries of phi are functions of t and the entries of u are functions of t. We're going to plug this into x prime equals ax plus f, because what we're looking for is a particular solution that exists because the system is non-homogeneous. Since x is equal to phi times u, and those are both functions of t, when we find x prime, we're going to use the product rule. So we have phi prime times u plus phi times u prime in place of x prime. Fleshing out the system then, we have in place of x prime, phi prime times u plus phi u prime. And that's going to equal a times x, but x, as we surmise, has the form of phi times u, and we'll leave f unchanged. We've already reasoned that phi prime is equal to a phi, so we can replace phi prime in the equation using a phi. We end up with a phi times u plus phi times u prime is equal to a, I'll drop the colors now, phi u plus f. A phi u is on both sides, so we can subtract it out, and we have phi u prime is equal to f. Because phi has an inverse, we can multiply phi by the inverse to get the identity on the left, and we end up with u prime is equal to phi inverse times f. Notice I'm multiplying by phi inverse to the left of f because I multiplied phi inverse on the left against phi times u prime, and order matters when we're multiplying matrices, so it has to keep the same order. Now we have an expression for u prime. Integrating that will give us u. So u is the integral of phi inverse times f. Remember, it's f of t times dt, and phi is also functions of t, right? Yeah, now we've just put a matrix product into an integral. How do you integrate a matrix? Well, first, remember, when we multiply a matrix by a vector, we get a vector. It's a vector. How do we integrate a vector? You integrate all of the entries. Now looking back up here, xp is equal to phi times u. So xp is phi times the integral of phi inverse times f of t dt. I don't really recommend that you memorize the process. I do recommend that you memorize this result. Putting it into context, we have that x of t is equal to phi times c plus phi times the integral of phi inverse f of t dt. that phi times c is our x sub c, the complementary solution, and then that phi times the integral is our particular solution. I'm going to stop the video here for time, not because this one's getting long, but because in the next video we're going to see how it's used, and that's going to take a few minutes.